Hey everyone. Okay, welcome to class. Let's see. Is my audio running? Always I want to check. Yes? Okay, good. Okay. It's always hard to tell with these online classes whether people are here. I mean, I'm just used to teaching a real class where you kind of just wait for everyone to finish walking in the door. But now I can't see. What I usually do is I'd poke my head out to see if anyone's walking down the hallway. But now you can't tell if someone's just like almost joining on Zoom or not. Well, hopefully people are here. Okay, great. So we're going to continue from where we left off last time. We were doing an interesting problem where we were trying to count something. It started out being easy, and then it got harder, and then it got into some very strange territory where we were counting how many 4-digit numbers there were, for which there were no equal digits next to each other, and the number was even. And somehow, at the beginning it seemed like this might be a reasonable problem, and then it looked like an unreasonable problem, and then somehow the answer turned out to be amazing. So let's dig in a little bit about this. First of all, I'm going to remember what was the question. The question was the number of 4-digit numbers, no equal digits next to each other, and also even. Okay? And we found out that the answer to this question seemed to follow some very mysterious sequence. And just to refresh our memory of where we were, what we found out was a good way to do this would be to let us define somehow E sub n to be the answer for the number of n-digit numbers and even. And my ... here is just referring to the no equal digits next to each other. We have to have that as well. Oh, I just realized I should leave the chat open, so I'm just going to put it here. As usual, if you have any questions or any comments, just type raise hand or RH into the chat, and it'll be fine, and I'll see it. And we also defined this ON to be the same thing, number of them where it's odd. And what we found out is that there are some nice things for this recursion. We found out that E sub 1 was equal to 4. It was 2, 4, 6, or 8. And we found out that O sub 1 was 5. 1, 3, 5, 7, or 9. And then we had some kind of a recursion as well. We knew that E sub n plus 1. Can anyone help refresh memory? What was this? Type a RH or a raise hand or a raise. Activate.
So like to get n plus 1, you make an even, you make an en, and you have 4 ways to do this.
Okay, if you don't, yep.
ON.
Let me just refresh that over here. So it's like if I have an n-digit part over here, and then we put one more digit at the end, and this is even. You said one of the cases is where your n-digit, this arrow is supposed to go all the way across to the right. Okay, it's like, that's just terrible. That's a terrible picture. I'm going to do a better job. So I want to say here I have an n-digit number, and I want it to be clear the arrow goes all the way across, and it happens to be even. And if I want the last one to also be even, I'll just write the E for that. Then Edivate, you said the number of ways to do this was En times how much? 4. Because if it's already even to begin with, the number of ways I can finish off with an even number at the end, which is different from the one I've already used, is 4 out of the 5 even digits. And the other opportunity is if you had this n-digit number, and it ended in odd, but you still want it to end in an even number, this would be ON times, and this was 5. So then we found out there was this nice recursion. En plus 1 was 4En plus 5. I'm going to write a dot there, just because otherwise it looks like 50 sub n, and I just want to emphasize that's an O, not a 0. Capital O is a terrible choice for variable names, but I guess we're stuck with that. You see, if I'd use lowercase, if I use lowercase, then it would be okay. It would be like a lowercase o, and that's okay. Except that if I have a lowercase e, that's 2.718. So you lose both ways. All right.
A fancy O with little squiggles somewhere.
Fancy O with a little squiggle. Thank you very much. Let's do that. Is that how you write cursive? I don't know. Actually, do people still learn how to write cursive in elementary school? Did you guys learn how to write cursive in elementary school?
I didn't.
You didn't? Some people do, some people don't. So, I mean, I actually have a first grader, and it's really funny because she's doing all the learning online. So my first grader is not actually handwriting anything. She's just typing. So that I've just realized that there's going to be an entire like category of people who grow up with Zoom school during their early elementary who never learn penmanship, which is going to be quite interesting. All right.
If you learn LaTeX in 4th grade, it's okay.
If you learn LaTeX in 4th grade, it's okay. I love it. This is the Carnegie Mellon audience. Okay, but I did this on purpose because, you know what? That's true for the en. And we're going to go and prove some formula. We're going to have fun with that. But I also want to say, something just wants me to put something else here, okay? I have E1 equals 4, O1 equals 5, recursion for En plus 1. Can anyone suggest something else that would give poetic justice to put in this space? I want to give more people a chance. Braden?
Well, it'd also be nice if we had a formula for O of sub n plus 1.
Why not? On plus 1. But what would that be? Let's let somebody else go, okay? I want as much different participation as possible. Aha, Subhashish.
Mine would be very similar to the en, so it'd be 4 ON plus 5 EN.
Okay, 4on plus 5en. Now, important thing here is like, why did we have to change the on and the en? Well, it's because if I think about the picture, if what I want instead is, suppose I want to end in an odd, okay, so now it's ending in an odd. If it happened to be odd to begin with, then that would be on times 4, because out of the 5 odd digits, we ate one of them already. Is that okay? All right. So I have this en plus 1, this on plus 1. I've got this 4en plus 5on, 4on plus 5en. This is indeed one way to write this. But I want to twist it a little bit. The way that if we ever have like systems of equations or anything, we often like to write the same variable in the same column. So I'm going to take what you have here and simply flip it around, and I'll write the 5en plus 4on, just for kicks. Is that okay? It's the same thing. So let's flip it around. 5en plus 4on. Okay. Now, why would I have done that? Now at Carnegie Mellon, we have an interesting university in that freshmen often take like a bunch of different classes, okay? But in many other universities, one of the freshman classes is like the fundamentals of calculus, if you want to be a math major, which is like how epsilons and deltas and all that work. In Carnegie Mellon, we actually switched things around, and we put a different class into the beginning, which not every university learns at the first semester of freshman year. And that other class is something that might give you another insight to this particular pair of equations. That's a hint. Does anyone know what I'm getting at? I want to go and use a different area of math. Oh, I already see it. Somebody put in John S. Matrices. John, could you please elaborate? What do you mean by matrices? Uh-oh. I'm afraid that I'm having trouble hearing you. Get a matrix for this system of equations. So let's rewrite this thing as I'll do the easy part, which is the vector en plus 1, o n plus 1. That was supposed to say on plus 1, but it's unreadable. Let me try it again. O n plus 1. Okay. And that's equal to something. So now I need to set up some kind of a matrix. RH, raise hand. We've got Ising.
So maybe we can write like a 4, 5, 5, 4.
Aha.
Times like a 2 by 1 matrix, which would be like en and on.
Thank you. En and on. Okay. So this is actually true. And in fact, I guess you don't have to have taken a Carnegie Mellon linear algebra class. Most people actually learned this at some point in high school. And if you remember in high school, at least how I was in high school, when people said, here's how you multiply matrices, I said, what kind of crazy person invented this dumb way to multiply matrices? I have a better way of multiplying matrices. You just take the element over there, and you multiply it by the element in the same place over there. I don't know if anyone else had this feeling of like, why don't we just multiply matrices like element by element? Well, there's a reason. It's because it actually helps you encode more sophisticated behavior. And what you're seeing here is one direct application of why that's a useful formula for multiplying matrices. Actually, that's a linear transformation, as we learned in these real linear algebra classes. So it turns out that actually, if I wanted to know En and On, there's a way to do it using matrices. What's this? Ah, Chris has some idea. What is this? Chris, what do you think?
I was asking just how is the matrix multiplication formula intuited or derived?
Yeah.
Like, why would you get to do it that way?
Why would you think to do it that way is a great question. So I guess one intuition that I would give, okay, this is not a linear algebra class, but we will now go and take a side step into that direction. Here's what I would say. If you knew the On and the En, that's like your two values of where you are right now, and you want to know where you are at time n plus 1, a linear transformation means that each of those new coordinates, the En plus 1, the On plus 1, depend linearly on the previous ones. Linear transformation means that it won't be like, well, if I had these two values before, to get the next value, I'm going to take one of them to the power of the other one. So the point is, like, you can imagine I've got like two numbers and I've got some machine which will give me two more numbers, but the only thing it's ever allowed to do is linear stuff. Then actually this idea is quite natural, because what this is telling you is it's telling you I'm going to use those coefficients on the inputs. I mean, I'm not saying this is the best answer, but I'm just giving an example of like why this might actually make sense. And yes, indeed, and you can also compose linear maps in this way. So the beautiful thing is if you do it this way, then if you want to do it twice, then you actually just do the matrix multiplication. Thanks for asking. This is actually not a linear algebra class, so I can't go deeper in that. Although I will say, if you're curious about that, I actually have a YouTube video which I did out like a year ago for Math for America. It's a group of teachers which actually explains that the title of the talk is something like Why Matrices, and it goes into all of this detail of why you make the matrix multiplication the way it is. So I've got that, but we'll do that. You can see that another time. And the beautiful thing about YouTube is like now, well, it's there now. so in some sense, if I teach something, it's just like it's there. So you can find that. Okay, but why did I get so excited about this? Oh my gosh, how are you guys so fast? Anyway, so like if you have this, you actually now have a magic way of finding En and On. And now this is like getting into the fact that there is this other class. Here's where I'm going to say, matrices are going to be useful at some point in a very real way in this course. If you haven't yet taken a class in matrix algebra or linear algebra or matrices and linear transformations, if you're still taking it now, don't worry. By the time we need it in this class, you will have gotten to that point. And if you've already taken it, then okay, great, you already know some of this stuff. But why is this useful? Subhashish. Yeah, you can take the power of a matrix. So for example, if I wanted to know E4 and O4, what would that be? E4 and O4, well, I would just need to take the 4, 5, 5, 4 times, I'm going to use yellow because I'm about to replace it, E3O3, right? And if I wanted to do this, well, what's E3O3? I can open that too. So that's equal to 4, 5, 5, 4. The E3O3 is going to become another 4, 5, 5, 4. And then that's going to go into an E2O2. So actually, if I keep doing this, I'm actually just taking a power of a matrix. That's really cool. Because you see, matrix multiplication is associative. That's amazing. And so I can just like multiply these matrices first. So in general, what I get is that it's going to run into me, so I'm going to have to use a new screen. I'm about to flip to another screen. This is going to give me, in general, ENON is equal to 4, 5, 5, 4. Can someone help me finish? I want to write something, and it's not this. What else can I do? Out of it.
You can say it's 4, 5, 5, 4 to the n minus 1 power times E1, O1.
Yes, it is.
And like we know those numbers.
Yes, and we know what E1 and O1 are. Okay, E1 and O1, oh yeah, we know what they are. Let me just write an equal sign because I'm going to just write it all out. 4, 5, 5, 4 times E1 was 4, O1 was 5. Okay, well, oh no, I missed the power. The power needs to be here, n minus 1 power. Okay, that's ugly still though. It turns out there's something very, very convenient. Did you know that I can get 4, 5 in a nicer way? Fun fact. If I want to get 4, 5, I'm going to write an equal sign. I can use 4, 5, 5, 4. I just got lucky. The numbers are nice. I'm missing something here, so I need to write another thing to multiply it by. Can anyone tell me what that is? Subhashish, did you just raise your hand?
Yes. 1, 0.
I think so. Yeah, let's do that. So if I did 1, 0, my matrix multiplication, the 1, 0 gives me 1 times 4 plus 5 times 0. That's 4. And I get on the bottom, I get 1 times 5 plus 0 times 4. That's 5. How convenient. So now I have a beautiful formula. 4, 5, 5, 4 to the power n times 1, 0. Okay, now that's satisfying because it's just to the power n. And now the question becomes, how could I raise something to the power n? I wish I could know a good way to take a matrix and raise it to some power. Is there a way to do that? Brandon.
We probably want to diagonalize the matrix.
Diagonalize the matrix. Okay, so now at this point, we're going into things which I know there are probably some people in this class who have not taken that part of the linear algebra yet. So we're not going to assume you know that now, but we're going to use this like a lot later, like in about a month or two. And so it turns out that there's a standard way to take powers of matrices, and it's based on something called diagonalization. The easiest way to think about how diagonalization works is to here I'm trying not to teach you the whole diagonalization, so I'm going to show you some very fun, interesting coincidences that just happen to work for this matrix. So it just so turns out that 4, 5, 5, 4 is the kind of matrix for which you can see the eigenvectors and eigenvalues. If you have never learned that word before, don't worry, we won't need it really now. That's why I'm not writing it down. I'm just going to write some fun facts. If I multiply this by 1, 1, what do you get? It's nice. It gives you 9, 9. And the way I'm going to write this is 9 times 1, 1. You may already know this from a linear algebra class, or you'll learn it soon, that not in this class, but in some other class, that this is a very special situation. When you multiply the matrix by a vector, you get back the same vector, just rescaled. That's a cool fact. And there's another cool fact, which is that there's another thing you can multiply this by. This is just a lucky kind of matrix for which I can find two of these things that I can multiply by where it's just rescaled. Actually, can anyone else see it? This is not how you normally diagonalize a matrix, but I claim 1, 1 was nice. There's something else really simple that if I multiply it by, it ends up rescaling. Oh, I see a bunch of people have said something. Subhashish?
I think I've said it. -1, 1.
Negative 1, 1 also works, yep. So we could write like negative 1. I'm an optimist, so I want to write 1 on top. Is that okay? I'll start with the positive. So 1, negative 1. All right, so 1, negative 1. And if you do that, it gets to minus 1 times 1, negative 1. So these are like fun facts. And actually, the fact that I know both of these things lets me write down something a little bit interesting. Now I can actually write down a matrix product, which says if I took 4, 5, 5, 4, and just for the heck of it, multiplied by the matrix, which is 1, 1, and 1, negative 1, the answer ends up being, maybe I'm going a little bit too fast. This is like matrix multiplication. So how does this work if I do this kind of matrix multiplication? Can anyone help me out with that? Like, why did I bother to do like the green column and then the purple column? There's something nice about the way matrix multiplication works. Chris, can you expand a little bit more on that?
It's going to be the same two vectors concatenated.
Yeah. So the way it works is if you think about how you multiply matrices, if you wanted to know what you'd get in this outcome, if you want to do this, I'm just drawing a vertical bar. If you want to know what you get in this outcome, actually, you'll take like the left things, the green ones, the 1 and the 1, and then you'll do stuff with the green ones. And as you do the stuff with the green ones, that tells you what goes into the first column. So the important thing is actually the first column of the output is exactly that green stuff. This 9 times 1, 1, that is what goes in there. Is that okay? So I actually get 9, 9. It would be 9, 9. I guess I can write the 9, 9. But I want to remember it's 9 times 1, 1. Now, how about the other column? The other column gets the purple stuff. And the purple stuff would be minus 1 and 1. Okay. By the way, slow me down if this is not making sense. You can also raise hand if you have a question. I don't need only raise hands for answers, because otherwise it's a dangerous thing where I might go far too fast. So I'm just saying, okay, that's neat. If I multiply these matrices, I can get that. But there's something else really nice about this outcome. It turns out that you can write this outcome as what happens if you take a certain matrix. Sorry, the left matrix, I'm actually going to use the 1, 1 and the 1 minus 1, and I'm going to multiply it by another matrix. And I claim that this other matrix you multiply by has a form which is diagonal. So my claim is, this stuff over here on the left, that was just like multiplying matrices. And if I happen to have this 9, 9, negative 1, 1, how do I fill in these two missing blanks? It turns out that if you take a matrix and you multiply on the right by a diagonal matrix, it does something very nice. Can someone help me fill in the numbers? Isin.
Should it be like 9 minus 1?
Yeah, it should be like 9 and minus 1. And if you look at it, like the best way to understand this is to actually think about what you would do if you were trying to multiply these two matrices. If you try to multiply these two matrices, the 9, 0, look what happens to the 9, 0. If it goes across over here, the green stuff only hits the green stuff. That's why I'm using colors. Does that make sense? Like if you see this green 9 and the blue 0, once I flip it over, that's how I always think of matrix multiplication. The green stuff hits the green stuff, and the 0 just ignores the other part. So that's why if I do the matrix multiplication, the first column here is just this first column scaled up by 9. Okay? And then the second column of the output is what I get if I took the 0, negative 1 and multiplied it across. The blue 0 just, 0 times anything is 0. But then the purple minus 1 multiplies each of those by minus 1. what I'm emphasizing is, it is precisely because this was 9, it was a vector scaled by 9, that what I can write is that I can write the vector and I can write a 9. And because the other one was a vector scaled by -1, I can write the vector and I can write a -1. I want a quick check-in. Did this make sense? Are people following this? Because, by the way, what you're getting is you're basically getting like 2 weeks of linear algebra in approximately 15 minutes. So, so if this is making sense, this is amazing. It's a quasi-review is my hope, or if it's not yet a review for you, it's a preview where when you finally take it, you'll be like, oh my gosh, it's just this. Okay, what's the upshot? Why do we care? The reason we care is because you can now use the matrix inverse, and we actually have just diagonalized the matrix. Now what do I know? Now I know that if I want 4, 5, 5, 4, well, let's multiply both sides by, ooh, I see a question. Andrew, do you want, could you please say that again? Because I'm having trouble reading it.
Yeah, I was asking 9 and -1 and those vectors with them. Those are the eigenvalues in vectors. It's been like a year since I've done linear algebra. I can't remember fully.
Oh, you want to know what are the fancy words for these? Okay, yes. I was intentionally trying not to use fancy words because they scare people. But eigenvalues are the 9 and the -1. And the eigenvectors are these 1, 1 and 1, -1. The words are actually not important because what we're doing here is simply just with like mathematical stuff. But if you did take these classes like some years ago, this is what we just got. Thanks for asking. Anyone is always welcome to ask questions. But now why did I do this? I did this because I want to know what is 4, 5, 5, 4. And I can know that by just like multiplying by the inverse of this matrix. But remember when you do linear matrices stuff, multiplication is not commutative. So I need to multiply on the right-hand side. So I'm going to take this top equation, middle or whatever equation, and I'll multiply the right-hand sides by the inverse of that matrix. So now what I get is I get, why am I in white color? I guess it's okay. 1, 1, 1, -1 times 9, -1, 0, 0 times the inverse of 1, 1, 1, -1. Now, we do learn how to invert 2 by 2 matrices. I'm just not going to do the inverse yet because I want to stare at this. 4, 5, 5, 4 is equal to some matrix times a diagonal thing times the inverse of the matrix. Hey, what happens if I take the power now? What happens if I took this expression and I slammed it against a copy of it next to it? Out of it? Did you say what? Convenient stuff. Yes, it is convenient stuff. If I took this expression of these 3 matrices and I slam another copy of it on the right, do you see that canceling is going to happen? Because there's an inverse here, and the first guy is going to be slammed right next to it, and the inverses will cancel. So, in particular, if I took like the square of this, 4, 5, 5, 4 squared, I actually just have the same first thing. 1, -1, 1, no, there's a positive 1. 1, +1, 1, -1, times what I end up getting is 2 of these, 9, 0, 0, -1, squared, because there's 2 of them, and a 1, 1, 1, -1 inverse matrix. Did that make sense? The way this happened is I just took 2 copies of it, slammed them together, and I cancel the inverse and the 1, 1, 1, -1 thing. And then I end up having the middle parts hit each other to make a square. Does anyone want me to explain that one again, or is this good? There's no harm in slowing me down, but I guess we'll keep going. So the beautiful thing is like when you slam them together, cancel the inverse and the real thing, and you just like keep powering the middle. Now, why is that nice? How nice is it to take the power? How nice is it to square a matrix like 9, 0, 0, -1? Well, let's try. if I had a matrix like 9, 0, 0, minus 1, and I multiply it by itself, 9, 0, 0, minus 1, what happens? Christopher.
Yeah, so when you square, or in general just take the power of a diagonal matrix, you just raise all those terms on the diagonal to that power.
Yeah, if you look at what happens, if you even just try to do it, it becomes 9 squared, because the 9, 0 goes against the 9, 0, and 9 times 9 is 9 squared. And then, like, all the other stuff just, like, is useless. Like, the 0 minus 1 going with the 9, 0, the zeros all hit the non-zero things, and you get, like, a 0. And the same thing happens on the bottom left. And on the bottom right, you get negative 1 with the negative 1, so you get negative 1 squared. By the way, is it a good thing that I'm seeing powers of 9 and powers of negative 1? Remember we had some formula for this answer that we guessed? What were the two big things in that formula? There were 9 to the power n's and there were minus 1 to the power n's. This whole thing is coming together, right? So we're actually getting the whole thing. All right, so in that case, if that was to the squared, I need to know what is to the power n. Well, it's just like replace the 2's with n's, okay? So now I'm going to write down what I know, this 4554. 4554 to the power n is equal to, we've got some like 1, 1, 1, negative 1 times 9 to the power n, 0, 0, negative 1 to the power n, times the inverse of 1, 1, 1, negative 1, inverse. Okay, I know that. And I also know something else. I know the formula for ENON. Is that what we had? Yes, the ENON formula. I'm just going to copy it. I also know that the ENON formula is just equal to, I'm supposed to take 4554 to the power n and multiply it by 1, 0. Okay, we are now almost done. Can anyone else suggest for me what to do next? We're only a few steps away from getting EN. I want to let more people participate. Anyone else want to throw in an idea of what to do? Venkatesh.
You can substitute that expression in, and then now you can work out the matrix products, because you'll have 1, 1, 1 minus 1 inverse times 1, 0.
Yeah. Let's do it. So I'm going to write this thing. I'm going to put the zeros in blue because they're just 0. We've got some inverse to deal with. How do you invert a matrix? 1, 1, 1, minus 1, inverse, and 1, 0. Okay. So you said we've got to do some calculation at the end. Let's start taking it apart. How do you invert a 2 by 2 matrix? Anyone want to help me do that? Just like hit a raise hand. Two by 2 matrix inverse. There's even some formula for this, I think. Isain, were you going to tell us how to do that?
So we calculate the determinant.
Okay.
Yeah.
Quick.
So we do calculate the determinant of the matrix itself,
What is that?
which will be like we do the product with two diagonals. So like 1 times minus 1 minus 1 and 1.
Yeah. So is it? Am I doing it right? I think. So the determinant is minus 2. And then what goes on here?
So we will have like a factor of like 1 over minus 2 the determinant.
Okay.
And then there is something that we use sign for. I think it's like I don't remember exactly. But I guess we will use gonna be like minus 1, 1, 1. Yeah. So like we're gonna switch the sign of the diagonal.
Okay, so there's some formula. Okay, there's some formula. Let's see if it works. The way I'll check your formula is I'll just try multiplying. 8, does it work? I'm having a bit of trouble. I don't think this is quite right because, by the way, I could be wrong too. Oh, no, this is totally good. No, it's not. Wait, can someone else help here? Is this right? I need help. This is a part of math that I have a lot of trouble with, which is called formulas. You think so? It's right? But if I multiply the matrices, it seems like if I try to multiply the matrices, I get 0 in the top left. Is that right? It's not. It's not. So there's, you see, I was just doing a spot check. I was like, hey, I've got this thing. What if I try to multiply the matrices together? The -1 and the 1 hits that, and I get a 0. So what? No, don't worry. What should we do? How do we fix it?
So the top right and the bottom left should be negatives. And then it's -1 on the top left.
Is that it? Now I'm just gonna check, okay? I'm just like, okay, multiply. Oh, good. Okay, so if I do the matrix product, I'm just doing it. I'm like, I get -2, which is good because I divide by -2. Great. And then the other one I get 0, and then the other one I get 0, and yeah, it's good. So the way I deal with formulas is I ask the class because someone here surely remembers it, and I just check it afterwards, which is cheating. But okay, so we can do this. So this is the inverse. Now let's start multiplying. I need to take that and multiply it by this 1, 0. I can do that. I don't need to ask for help for that one, I think. So if I do that, I get -1/2 in the front. And if I see what happens, I get -1, -1. I think, hopefully. Okay, and if that's the case, let's go simplify. That will give me 1/2, 1/2. Okay, now I just have to keep going. So I need to go and say the En is what I care about, which is the top of this. So I now need to take this 9 to the n, 0, 0, -1 to the n. That's over here. I'm running out of space. Let me write it as 1, 1, 1, -1, 9 to the n, -1 to the power n, 0 and 0, and multiplied by this 1/2, 1/2. Okay. Is anyone else like me very happy to see 1/2s? That was also in the problem, right? That was also in the conjectured answer. So if I now try to multiply this, what happens? I get 1, 1, 1, -1 times, what is this? I'm only drawing one vertical bar right now because I might have longer expressions. What is this 9 to the n, this thing, times the 1/2, 1/2? What happens? Raise hand. Issei?
So we will have like 1/2 times 9n.
Okay, that's a times sign. Times 9 to the power n. And?
And then 1/2 times -1/3.
Okay, let's finish this. All right. And so what's En? I have a formula. So how do you get En out of this? You just take that, and En's the top one, right? So you multiply across by the 1, 1. What happens when you take this thing with the 1, 1? You get the formula. So we end up getting that En is exactly equal to, take this guy, against 1, 1 just means add the two things together. So it's 1/2, 9 to the n, plus 1/2, -1 to the n, which is exactly what we wanted. Bam! Done. So that's what's going on here. I intentionally actually went and threw linear algebra and matrices at this because I just wanted to know, I wanted to let everyone have a feel for the kinds of, the range that we're going to be getting in this class. Like this class is not just going to do a bunch of like combinatorial things. We're going to be bringing in ideas from all over the different places. This is a preview of the kinds of stuff we'll be doing later. It is okay if you were not familiar with eigenvalues and eigenvectors before, because we won't need to use this kind of stuff until later. But the preview lets us see what's going to be here. Okay. So this is surprising. You can get the entire answer with this, and hopefully this also sheds some light on why anyone might care about diagonalizing matrices. It's actually useful. We have about 10 minutes left. With the next 10 minutes, question, Chris.
How often can you get explicit formula from recursive formula using matrices like this?
You are going to see lots of that in approximately 1 to 2 months. Maybe in about 1.5 months, we're going to be doing this kind of stuff in an extensive theoretical way. But I just did this opening one because it was like a very innocent problem. So the answer is a lot. And here's a meta answer. If we're teaching it in the class, you're going to see one. we teach you the ones that we have formulas for, if that makes sense. So, okay, great. I want to go on and now start talking about some things that might be a little bit more on the beaten path. I always use the first week of class to talk about some things off the beaten path on purpose, just to give an idea of what the class will be like. But now let's go and move back to things on the beaten path. The first one is I want to go to counting some things that people might have been used to counting before. And to do that, I'm going to draw a chart, I'm going to draw a diagram, and we're going to look at like the number of paths that we can take to go through some kind of a grid. So I'm going to draw this grid here. And it's going to be, it's going to look like a 4x4, except that I'm going to be walking along the edges. So if I drew something like this, here is an example of a path. That's an example of a path that goes from the top to the bottom. So a natural question could be, how many paths that always go down from the top to the bottom? That's a bit more on the beaten path of a kind of problem that one would see in a combinatorics class. Don't worry, we'll soon get off of the beaten path again. But this question is like, you're going from there all the way down to there. How can you do this? Well, this is a classic type of question. I have like 4x4 grid, and I'm taking all these different steps. And I see Brandon. Oh yeah, always go down means down to the left or down to the right. Yes, Brandon.
Can you do like a stars and bars sort of argument?
Ooh, is this a stars and bars argument?
Or kind of.
Okay, so there's some formula about stars and bars. We will actually come across that somewhere in this class, but it's not actually necessary for this particular one. Stars and bars is something to do with if I have like 3 different people I want to divvy stuff up among. Okay, we won't need that here. And somebody asked, is this like the King Kong problem on the homework? This has some relation. But I'm going to say it actually does have some relation to stars and bars, but we don't need to use that straight. Let's have some more thoughts. Venkatesh?
So you can consider a path as just like a string of different directions. So you can either go like to the left diagonally or like to the right diagonally. Okay. And the number of letters in the string will always be constant. So you can just kind of figure out the total number of ways to arrange that string.
Okay, so we're now talking about a string, and the easiest way to think of this is it's an instruction set. It's like saying do the LRRLLRRL, and that's how you go from top to the bottom. Do you see how I came up with these instructions for this picture? It's exactly what the picture shows. You go left, then you go right and right again, then you go left and left again, then you go right and right again, and you go left. So there's an instruction set for each path. I see there's a question or an answer. Andrew, did you have some thought?
I think that might like kind of fall apart halfway through because then you might be constrained like you can only go right or something.
Oh, so what you mean is like, wait a second, it's not really like all of the L's and R's you can do. Like what if somebody gave you instructions, go L, 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 L. Then it's like, nope, you fell off. Okay?
Is that you have a certain number of R's and a certain number of L's. And like that is constant, right? So like you can't have like 8 L's, you can have, you know,
Yeah.
like a, you can have like a certain amount.
You're going somewhere with this. So actually what you observed is that these are the instructions. For every instruction, you get one of these paths. But you've noticed that the instructions have certain rules. In particular, people notice there are 8 steps. You do 8 steps because you have to fall 8 times. But there's more than just 8 steps. It's more truth than 8 steps. There's 8 steps, but somebody said there's a specific number of L's and a specific number of R's. Is that true, and how many?
It's already in the chat.
Oh, it's already in the chat. Okay, I'm sorry. I just can't read. But so what did the chat say? Tell me what the chat said. Oh, I see. I can read now. It says, yeah, that's right. So Suvik said 4 L's and 4 R's. That's right. I have to apologize. I'm doing this from my studio where your words in the chat are like super small and giving me an eye test every time. That's why I keep asking people. But so what you actually have here is you have 4 L's and 4 R's. Okay? And that can be seen because if I'm going all the way down, I actually do have to do 4 L's and 4 R's. I have to do 8 things. You know what I mean? I have to do 8 steps to go down. And if I had too many L's, what would happen? I would be that way. And if I had too many R's, I would be that way. Yeah? So that's why it has to be equal, because I fell down 8 times. Okay. Now the question is, how many ways can I make an instruction set that has 4 L's and 4 R's? Raise hand. Charlie.
So you have 8 total, and you need to choose the 4 spots where you make, say, a left, and then have all the other ones be right.
Yep.
So I guess it would be like 8 choose 4.
Yep. So we want to know how many ways to arrange 4 L's and 4 R's. And what you said is, I have 8 spots that I put some letter in. So out of 8 spots, you have to pick 4 to be L's. And once I've done that, that defines the entire sequence of instructions. I have these 8 spots where the instructions will go. Bang, here go the 4 L's, and the rest are R's. And the number of ways to do this is equal to what we call 8 choose 4. And that's that's just how you write it. This is 8 choose 4. And how do you compute 8 choose 4? Anyone want to help me? Christopher? I see you have something. What did you say?
I just wrote in the chat, it's 8 factorial over 4 factorial times 4 factorial.
Yes. And the easiest way I usually think of doing this is I go and say, look, how many ways can you do this? Well, there's 8 ways to choose where the first position goes, or where the first L is. So it's 8 ways to choose where the first L goes, times 7 ways to choose where the second L goes, times 6 ways to choose where the third L goes, times 5 ways to choose where the fourth L goes. But then I have to divide by some stuff. So this thing here is like, out of the 8 positions, where's the first one for the L? Where's the second one? Where's the third one? Where's the fourth one? But I have to divide by the number of ways I can rearrange those positions. Okay? So I have to divide by how many ways I can rearrange these positions. Because if I went and told you, this one goes here first, and then the next L goes here, that's the same outcome as if the first L went here and the next L went to the original place. I see we're a bit short on time, so I promise you I'll go deeper onto this. I'll say this again next time. I'll say this part again next time, more carefully. But instead I want to use the last bit to do a slightly different problem because of there's some homework due on Friday. And so I want to make sure I talk about a different problem. And the different problem is, what happens if I have the same picture, except that I have a hole? When I say a hole, I mean this. So now how many ways are there to get all the way around? Notice that there is a hole. How can you do this now? Because now it breaks. It's no longer true that I can just use 4 L's and 4 R's. And it's no longer even true that I can just count how many L's and R's there are. There's just this random hole there. Aha, we have some more people. Dhruva.
I guess we could just subtract all the ways that do use that rule.
Yeah, we can do this by subtraction. And of course, there's so many interesting things about this problem that next time we're going to do it in another way also. But I just wanted to give this to you because there's some homework, right? So the answer here is equal to the number of ways before, which was this 8 choose 4, okay, minus the number of ways that specifically go through that bad spot. Does that make sense? So now I really want to go through that bad spot. Minus the number of ways that go via that missing edge. Oh, what's that? Now I need to draw that. How do I force myself to go via that missing edge? Before I draw a picture, it's like, what does that mean? How do I force myself to go through this missing edge? What else do you know then? If your path has to start from the top and it has to go through the missing edge. Can anyone tell me anything about the structure of the path? Insane.
So I was thinking like if you can start from there into the hole and then calculate from the hole into like the
Yes. So the point is, if I'm forced to go through this edge, then I first somehow have to get to the front of the edge. So the second part is how many ways are there if I'm forced to use the edge? Well, it will look sort of like this. I hope my picture sort of makes sense. This is my only land I'm allowed to walk on. Does that make sense? I'm like, I have to somehow start from the top, get to the front of the edge, take the edge, and then somehow finish. This is the answer to the yellow thing. It's the number of paths that go through this. And you know, maybe it's something like this. But what's that? How many ways here? How many ways are there to do the top piece, go to that, walk over that, and then do the bottom piece? Turns out to just reuse some stuff that we did earlier. Cindy, did you have something to add?
you can have enough ways to do the top, the parallel, and then the bottom.
Okay, do this one. And what do you do with those two numbers? Multiply them, that's right. Because anything you do on top, you can then do, you can follow it up with anything you do on the bottom. You multiply because we take any option there, and then we take any option there. And since I can do any of the first and any of the second, the number of ways is to product them. And now we're basically done. What is the number of ways on the top one? I don't need numbers. I want chooses. I actually hate numbers. I like just like what they really are. Charlie?
It would be 3 choose 1.
This is 3 choose 1 because it corresponds to an LLR rearrangement, right? So I've got 3 things. You could call it 3 choose 1. You could call it 3 choose 2. Both are fine. We'll talk about that soon, next time. Times, what about the right-hand side?
That 4 choose 2.
4 choose 2 because there's 2 L's and 2 R's. And so the answer to the whole question is 8 choose 4 minus 3 choose 1 times 4 choose 2. And that's where I wanted to make sure we got to by this point today. Sorry we went over time, but we'll continue next time and continue walking through all these different kinds of ideas. See you guys.
Thank you.
Oh yeah, sure.
Thank you.
Thank you.
Thank you.
Thank you.
Love you, bro.